Alright, today we will be talking about relationships between different molecules, particularly in stereoisomerism. And so to start off, we should probably know what a molecule is. Well, a molecule, as depicted in these models that we have here, provided to us by Miss White, a molecule is a bunch of atoms bonded together. And so the atoms in this case are going to be the different colored spheres, and the bonds are these gray objects in between those spheres. And so when we bond a bunch of atoms together, we can get molecules. Now, you can get a lot of different molecules from any atoms that you can bond together. However, not all molecules that have the same atoms are the same. Molecules that have the same atoms but are not the same are called isomers, and we can see two isomers here. So these are actually two different molecules. They're not the same, even though they have the same atoms. We can see that they all have two black and then one of these 6 rainbow colors for atoms. However, the orientation of them are different. For example, on the bottom, we can see that they're exactly the same. The purple, white, and yellow are in exactly the same configuration, as you can see from here. But at the top, they are not. In this case, the greens point down, but the blues don't point in the same direction, and the reds don't either. And so these are not the same atoms, because no matter how we rotate any of these bonds, let's say I rotate this one this way, in this case the red would match up, but the blue and the green don't. And so these cannot be two of the same molecules, and these need a classification based on the properties that they have relative to each other. And so what classifications do we have? There are a few types of isomers, but today we will be covering stereoisomers. Stereoisomers have atoms that have the same connectivity, meaning they're connected to each other in the same way. For example, this black atom on the top is connected to red, green, blue. This black atom is also connected to red, green, blue. And you can say the same thing for the bottom black atom. However, in stereoisomers, the 3D spatial arrangement of the atoms is different. This can be seen particularly in the top layer. In the top layer, the 3D spatial arrangement from red, green, blue on the left, or my left, your right, this one, the red, green, blue goes, you see it as counterclockwise. However, in this one, it is clockwise. And so that makes the 3D spatial arrangement different, classifying these as stereoisomers. Now, there are going to be 2 types of stereoisomers. I'll make the first one right now. These are pretty fun to play with, actually. Okay, anyway, the 2 types of stereoisomers are called enantiomers and diastereomers. The first example that I'll show you is going to be enantiomers. Shoot, oops. They're going to look like this. Now, you might be wondering, are these the same molecule? Well, let's try to look at them and test them out. Let's say we put the yellow to the back. We'll flip them like this. Are they the same molecule? Well, no, the red, green, blue go in different directions relative to each other. And so these 2 are going to be stereoisomers again because they have the same atom connectivity but different 3D arrangement. And so as I mentioned before, there are 2 types of stereoisomers. They're enantiomers and diastereomers. These 2 are going to be enantiomers. Enantiomers are mirror images of each other. That means if you draw a mirror line over here and imagine you reflect this all the way to this side, keeping the lengths between the atom and the mirror the same, because that's how a reflection works, you get the opposite atom. And so if I position them like this, you can see that these are mirror images of each other. If we draw the plane right here, everything maps to each other. The blue goes to the blue because it's the same distance from this imaginary line. The greens are the same distance from the imaginary line as well. And so these are mirror images of each other, or enantiomers. Note that one molecule can only have one enantiomer. If I flip this over here, you might think, well, doesn't that produce a different mirror image? Well, it does. However, let's say you do it like this. It's still going to be the same molecule after rotation. And so each molecule can only have one enantiomer. However, let's make our molecules more complicated again. Let's say we have the molecules that I presented at the beginning. Now let's say they look like this, where we have, again, the 2 black the 2 black atoms connected to 6 rainbow-colored atoms in total. So it would look like this. Now, we learned about enantiomers. Those are mirror images of each other, provided that they are not identical, of course. Are these going to be enantiomers? Well, let's see. How can we place these so that they are mirrors of each other? We can place them like this to make the bottom layer mirror images of each other, but the top just doesn't seem to work. Let's turn this like that. Yeah, it just doesn't work because these two aren't gonna look exactly the same. Well, the bottom two are going to be mirror images of each other. And so the molecules as a whole cannot be mirror images of each other, and so these are actually not enantiomers. However, they're still stereoisomers, as I explained earlier, so they must be the other type of stereoisomer called a diastereomer. Anyway, a diastereomer is anything that is a stereoisomer that is pretty much not an enantiomer. They are not mirror images, yet they have different connectivities. A molecule can have at most one enantiomer, remember, but they can have multiple diastereomers. For example, if I pay attention closely and try not to create an enantiomer, this is kind of hard, to be honest. Let's see, I switch the green and the blue on this one and see what happens. Well, we can match the top up, and then, well, we can also match the bottom up. So anyway, switching those two created identical molecules. These are not going to be stereoisomers because they are the same molecule. However, let's continue switching some of these. Note that we can only switch the ones connected to the top at a time, or connected to one atom at a time, because if I switch the yellow and the red atoms, they'll become connected to different atoms, meaning they're not stereoisomers anymore. Remember, stereoisomers have the same atom connectivity. Anyway, after flipping 2 of them, these are going to be diastereomers once again. But, and this is of course because they are not mirror images of each other. The top is mirrored, but the bottom is not. And to create enantiomers, what can we do? We already have the top 2 that are mirror images, so we can flip the bottom 2. Take a look at this. And voila, we have, well, yeah, 3D arrangement is kind of difficult. And these are going to be enantiomers of each other because, as I said before, we can draw this mirror line in between and everything maps to everything on the other molecule in a one-to-one relationship. All right, so now we'll be talking about the properties of the enantiomers and the diastereomers that we talked about previously. So in front of me, I have two enantiomers. These are mirror images of each other, so they are enantiomers. Enantiomers in general have the exact same physical and chemical properties between each other. For example, this includes boiling points, melting points, and all of this is pretty much determined by intermolecular forces. Those are forces that are in between molecules. For example, in between molecules that are this kind or in between molecules that are this kind. And those intermolecular forces are going to be the exact same because, of course, we can just take a mirror image of one force, for example, and it turns into the force of the other molecule. And so because our world pretty much has reflectional symmetry, if we reflect our whole world around like a plane, the physical laws will still be exactly the same. So these enantiomers will have the exact same properties as each other. Barring rotational things, which we won't talk about today. But anyway, the boiling point, melting point, other properties include its ability to react with other chemicals, particularly ones that do not have stereoisomerism. But the ones that do have stereoisomerism is, again, like another story. Anyway, in general, you should remember that enantiomers, because they are mirror images of each other and they're identical after being reflected, do have the exact same properties as each other. Now, diastereomers. We can create a diastereomer by switching 2 of these molecules in the enantiomer. this creates a diastereomer. Diastereomers do not have the same physical and chemical properties as each other because the interactions between, for example, atoms just in this molecule is different from the interaction between the atoms in this molecule. We see that if we keep it in this configuration, for example, the red and purple molecule atoms are going to have interactions with each other. However, when we look at the other side of the molecule, the yellow and blue on the left atom you see have interactions, whereas the white and blue have interactions over here. And so this affects the stability of the molecule, making one molecule more stable than the other, even in its most stable state. And of course, this affects the reactions that these chemicals can undergo. If, let's say, like the relationship between the green and yellow was important, well, this would create, let's say, like the reaction just deletes them. Okay, this is like an elimination reaction, except it would form a double bond. But yeah, this would still create a different molecule. Notice that this molecule is still not an enantiomer. It's still going to be a diastereomer, which is very interesting. And this goes on to prove the fact that because these are diastereomers, these still do not have the same properties even after the reaction. And so diastereomers tend to stay diastereomers, which I kind of just found out because I didn't plan this lecture beforehand. All right, let's get started with a real-world application. On my left over here is a big molecule that I made today in Miss White's class. It is ibuprofen. Ibuprofen is the drug that helps to treat pain. It is a pretty good painkiller, and it is also used to treat arthritis. So how does this relate to stereoisomerism? Well, let's first look at the molecule. The molecule looks rather complex. We can notice different groups that are unique to different molecules. This would make over here, this would make this a carboxylic acid. But other than that, it's very disordered. However, one thing to note about ibuprofen is that it actually has a significant amount of symmetry. For example, all of these molecules at the bottom, or atoms at the bottom, sorry, they're all they all possess the same types of patterns. For example, this black atom is connected to 3 white atoms, and then this black atom over here is also connected to 3 white atoms. And so a significant amount of symmetry can be seen in ibuprofen, and that is reflected in the amount of stereoisomers it has. So ibuprofen actually only has 2 stereoisomers. It has this stereoisomer plus this stereoisomer's enantiomer. Ibuprofen actually has no diastereomers, and that is because of how much symmetry it has. Of note, the enantiomers all depend on this singular atom over here. Currently, the molecule that I'm holding is designated as S-ibuprofen. The S, the letter S, is the designation for this enantiomer. The other enantiomer is going to be designated with the letter R, and that would be R-ibuprofen. I'll make that right now. So when I switch these two groups, R-ibuprofen is made. And to the naked eye, R-ibuprofen and the S-ibuprofen I originally started with, they look completely the same. Unless you're inspecting every atom, you can never tell that these are different. Anyway, I still haven't really said how this relates to anything. This relates to things because S-ibuprofen is the ibuprofen that actually works to treat pain, but R-ibuprofen is completely inert. I said before that enantiomers have the same physical and chemical properties, so you might be confused. But this is one of the exceptions that I pointed out. This is when a pair of enantiomers interacts with a molecule that also has stereoisomerism. That causes different interactions to occur based on the location of the atoms, the 3D spatial orientation. So the pain, I guess the pain molecules would have stereoisomerism since it is affected by whether it is R, or well, this is R-ibuprofen, or if we used S-ibuprofen. But anyway, this small change, just these two groups over here, just this molecule, or just these 4 atoms, and just this one atom, makes all the difference. If chemists did not know about enantiomers or diastereomers, ibuprofen would might not have been found? What if chemists only like found this one? They didn't know that flipping these two would make different results. What if they didn't know that enantiomers can actually have different results when treated with molecules that also have stereoisomerism? All of that would have made making these drugs much harder. I'll make this back into S and S ibuprofen right now. My point is, like, just these small, minute changes to a molecular structure may make all the difference. Drug making is like a terrifically difficult job. It takes thousands and thousands of hours for a single molecule to like pass the first few tests by like the CDC or something, and it just takes so much effort for drugs to be put into the market. And it is just all of these tiny differences that make that just decide whether a drug works or not. For example, maybe like when you're attacking an enzyme that is something that you want to get rid of, only a specific shape of a molecule might fit into there. When you reflect that shape, it might not work. And that is where enantiomers differ. Although enantiomers, like when you just heat it up and it boils or it melts, they have the same properties. The fact that they don't have the same reactions with other molecules with stereoisomerism is just incredibly important until today. And so, yeah, chemistry is full of exceptions, but it's just so cool. That was probably a very long lecture. I kind of enjoyed talking about stuff. But yeah, thank you for watching. I'll be very surprised if you watch to the end. So, all right. Bye.